The physical foundation of electrical grid stability is collapsing. Historically, massive spinning rotors in coal and gas plants provided immediate mechanical resistance to frequency drops. Replacing these thermal units with solar and wind removes this critical rotational inertia. A single 500-megawatt coal unit provides approximately 2,500 megawatt-seconds of physical kinetic buffer. Without this buffer, sudden supply drops cause rapid frequency collapse, risking widespread blackouts. To prevent instability, operators must deploy massive, free-spinning synchronous condensers to mimic this lost mechanical inertia. This has triggered an exponential demand curve, with required capacity projected to scale from 1,200 megavars in 2018 to 25,000 megavars by 2030. In highly decarbonized markets like Texas and the United Kingdom, minimum inertia thresholds are already breached regularly. Operators are forced to curtail cheap wind power or pay high premiums to keep fossil-fueled plants spinning solely for their mechanical weight. The supply chain cannot keep pace with this sudden demand. Manufacturing utility-scale synchronous condensers is highly consolidated, controlled by an oligopoly of 4 firms. Siemens Energy, AB, GE Vernova, and Ansaldo Energia command over 85% of the global market. Average procurement lead times have tripled, rising from 12 months in 2018 to 34 months in 2024. Projections show lead times reaching 38 months by 2026. Factory capacity utilization has surged to 96% and is approaching total saturation. This leaves zero margin for manufacturing errors, design revisions, or testing delays. The result is a severe structural bottleneck. Grid modernization and renewable integration projects worldwide are stalling because the physical stabilizers cannot be built fast enough. This manufacturing delay is driven by highly localized material and engineering bottlenecks. The primary constraint is grain-oriented electrical steel, which is also consumed heavily by the booming transformer sector. Electrical steel lead times have surged to 48 weeks, with costs rising 85%. Furthermore, forging the massive rotor shafts, which weigh over 50 tons, requires specialized heavy hydraulic presses. The global queue for these critical forgings has expanded from 26 weeks to 72 weeks. Finally, these rotors must spin at up to 3,600 revolutions per minute. Dynamic balancing to prevent catastrophic vibration requires highly specialized facilities that are now completely booked. These physical constraints in metallurgy, precision machining, and testing mean that capital alone cannot resolve the grid stability crisis. The transition to renewable energy remains fundamentally bound by the limits of heavy industrial engineering. Advanced semiconductor manufacturing is hitting a hard physical limit at the molecular level. The transition to gate-all-around transistors and three-dimensional DRAM requires atomic layer deposition. This process relies on highly volatile organometallic precursors to build silicon layer by single-atom layer. Global demand for these high-purity precursors is scaling exponentially. Volume requirements are projected to reach 360 metric tons by 2026. This represents a 200% increase from 2019 levels. A structural supply deficit emerged in 2021 as chemical synthesis capacity failed to keep pace. By 2026, the market faces a projected 95 metric ton shortfall. This deficit is compounded by a severe logistics bottleneck. Specialized, temperature-controlled shipping cylinders now require 52 weeks to procure, up from just 8 weeks in 2019. Supply chain for these critical chemicals is highly consolidated. Over 72% of global 9N purity precursor synthesis occurs in South Korea and Japan. This geographic concentration creates an extreme single point of failure for global chip makers. Only 13 facilities worldwide are qualified to synthesize and purify these compounds to the required standard. This standard demands a purity of 99.9999999%. The United States is highly vulnerable, holding just an 8% share of global synthesis capacity. This entire domestic supply is concentrated in a single facility. Any localized disruption in East Asia would immediately halt advanced logic fabrication worldwide. Capital expenditure in domestic fabrication plants cannot bypass this geographic chemical bottleneck. The bottleneck is governed by unforgiving laws of materials science. At sub-3 nanometer geometries, trace metal impurities exceeding 100 parts per trillion degrade gate dielectric breakdown voltage by over 26%. This drops the breakdown voltage from 12.4 to 9.1 megavolts per centimeter. Consequently, Achieving 9N purity is a non-negotiable requirement for advanced fabrication. Allowing impurities to rise to just 100 parts per trillion causes average wafer yields to plummet from 94.2% to 68.5%. This yield drop renders high-volume manufacturing economically unviable. Purification requires multi-stage fractional sublimation and vacuum distillation. As purity targets scale from 6N to 10N, production throughput decreases exponentially, locking the industry into a high-cost, low-yield chemical processing bottleneck. The Port of Hamburg is facing a severe hydrological crisis. Modern ultra-large container vessels require a design draft of 16.5 meters. However, Hamburg's actual permissible tidal-independent draft fell to 12.9 meters in 2024. This physical deficit of 3.6 meters forces megaships to lighten their loads before entering the Elbe River. The average lightning penalty has risen to 3,800 containers per transit. This double handling adds up to €420,000 in operational costs per voyage. Relying on high tide to navigate the river is no longer a viable workaround. The tidal-dependent transit window has compressed to under 120 minutes per cycle. This narrow window severely restricts vessel scheduling and creates systemic maritime bottlenecks. This crisis is driven by a self-reinforcing physical phenomenon known as tidal pumping. Deepening the Elbe River channel has paradoxically accelerated siltation. The flood tide now travels upstream faster than the ebb tide can flush sediment back out. Annual sediment removal volumes have more than doubled since 2016, reaching 34.8 million cubic meters in 2024. The tidal pumping index has risen to 1.45. This indicates that 45% more sediment is carried upstream than is naturally cleared. The financial cost of combating this physical feedback loop is escalating rapidly. Annual dredging expenditures reached €178 million in 2024. This represents a structural fiscal burden growing at nearly 8% annually. The physical limitations of the Elbe are causing a major structural shift in European logistics. Hamburg's container throughput has contracted by over 22% since 2019, falling to 7.2 million containers. Deepwater competitors like Rotterdam and Antwerp are absorbing these diverted volumes. Meanwhile, the Baltic hub of Gdansk has expanded its throughput by nearly 79%. This regional shift bypasses the German port entirely. This cargo diversion is exposing severe bottlenecks in land-based infrastructure. Rail transit times from Baltic and Adriatic ports to southern Germany have increased by an average of 36 hours. The physical limits of inland waterways are now destabilizing the broader European rail network. Modern jet engines operate under thermodynamic conditions that exceed the physical limits of their own structural materials. Turbine inlet temperatures in advanced propulsion systems now reach 1600 to 1650 degrees Celsius. This is up to 300 degrees hotter than the melting point of the single crystal nickel-based superalloys used to cast the turbine blades. To survive, these blades rely on a microscopic ceramic shield. A layer of Yttrium-Stabilized Zirconia, just 100 to 250 micrometers thick, must drop the temperature by up to 300 degrees. This thin barrier is the only thing preventing immediate structural failure. If this coating fails, the consequences are instantaneous. Ingestion of environmental dust or localized cracking causes the ceramic to flake off. Exposed to raw combustion gas, the underlying superalloy melts within seconds, destroying the engine. The supply chain for this critical ceramic is highly concentrated and geopolitically vulnerable. Refining raw zircon sand into aerospace-grade zirconia requires reducing hafnium impurities to under 100 parts per million. China controls 58% of this specialized purification capacity. The primary Western alternative is Saint-Gobain in France, which holds a 22% market share. This leaves Western defense and commercial aerospace manufacturers highly exposed to unilateral export restrictions on precursor materials. The vulnerability is even more acute for the stabilizing agent, yttrium oxide. This heavy rare earth element is essential to prevent the zirconia from undergoing catastrophic phase changes during thermal cycling. China controls over 85% of global yttrium separation and refining capacity, creating an absolute single point of failure. Even if raw material supplies are secured, the physical capacity to apply these coatings is severely constrained. The industry standard for depositing high durability, columnar ceramic structures is electron beam physical vapor deposition. The machinery required is highly complex, expensive, and produced by only a few specialized German firms. Lead times for these multi-million-dollar coating systems have nearly tripled, rising from 12 months in 2018 to over 32 months in 2024. This delay is driven by a global manufacturing bottleneck at firms like ALD Vacuum Technologies and Von Ardenne. The active global order backlog has reached a record 41 units. This surge is driven by simultaneous production ramp-ups for commercial engines like the LEAP and advanced military propulsion programs. The physical limit of high-vacuum engineering is now directly pacing the deployment of next-generation aviation hardware. Global steel production is facing a severe metallurgical supply shock. In March 2024, Cyclone Megan forced the suspension of operations at the Groote Eylandt Mining Company in Australia. This single event instantly removed approximately 10% of the global high-grade manganese ore supply. High-grade ore spot prices reacted immediately. Prices surged from $4.30 to over $8.50 per dry metric ton unit by the second quarter of 2024. Alternative producers cannot easily bridge this gap. Gabon's Monda mine scaled production to 8.5 million tons, but logistics bottlenecks on the Transgabonese Railway capped export capacity. Consequently, global inventories have depleted rapidly. Port stockpiles in China fell to a 5-year low of 4.2 million tons in mid-2024, as smelters consumed reserves to sustain operations. Smelters cannot simply substitute low-grade ore for high-grade oxide ore. Dropping the feed grade from 44% to 35% manganese triggers severe thermodynamic penalties. The slag-to-alloy ratio increases by 76.9%, requiring massive thermal energy to melt waste material. This chemical shift drives up power consumption. Electrical requirements escalate by over 20%, rising from 3,600 to 4,350 kilowatt-hours per ton of silicomanganese. This surge severely threatens smelter margins in high-tariff energy markets like Europe. Furthermore, the acidic slag generated by low-grade ore accelerates the chemical erosion of carbonaceous furnace linings. The operational lifespan of these linings drops from 60 months to just 36 months. The cumulative result is a 28.4% increase in production costs. Smelting silicomanganese rises from $950 to $1,220 per ton, establishing a high global price floor for steel. The high-grade ore deficit is compounded by structural logistics failures in South Africa, the world's largest manganese producer. Systemic locomotive shortages and copper cable theft have crippled the state-owned rail operator, Transnet. Rail's share of manganese exports has collapsed from 84.6% in 2019 to a projected 45.1% in 2024. To bypass the failing rail network, exporters have turned to heavy road haulage. Trucking ore over 1,000 kilometers to coastal ports has surged to 9.5 million tons. This shift adds a premium of $45.50 per ton over rail transport. This logistical pivot also carries a heavy environmental penalty. Relying on diesel trucks increases the carbon footprint of South African ore by an estimated 300%. This exposure will trigger severe financial penalties under the European Union's impending carbon border adjustment mechanism. Advanced metallurgy is constrained by a rigid physical byproduct loop. Selenium is recovered exclusively from the anode slimes of electrolytic copper refining. This makes the global supply of selenium entirely inelastic. Between 2020 and 2023, average selenium prices surged from $42 to $110 per kilogram. This represents a price increase of 161.9%. Yet, global refined selenium output grew by only 6.09%, rising from 3,120 tons to 3,310 tons. The physical yield is capped by the mineralogy of copper ores. Smelters extract only 2.0 to 2.5 kilograms of selenium per 100 metric tons of refined copper. Consequently, industrial consumers cannot incentivize higher production through capital alone. This inelastic supply chain directly threatens the production of electrolytic manganese metal. Manganese refining relies on an aqueous electrowinning process that is highly inefficient. Without chemical additives, the current efficiency of the electrolytic cells is only 30.0%. Introducing 1.0 kilogram of selenium dioxide per metric ton of manganese alters the cell chemistry. It increases current efficiency to 61.5%, effectively doubling production throughput. This chemical addition also drops specific energy consumption by 43.5%. Power requirements fall from 8.5 to 4.8 kilowatt-hours per kilogram of manganese. Operating a refinery without selenium is economically impossible. The resulting power demand exceeds 8.0 kilowatt-hours per kilogram. Under current global electricity tariffs, this energy penalty forces immediate facility closure. The geopolitical concentration of this chemical loop creates an extreme single point of failure. China controls 92.5% of global electrolytic manganese refining capacity. Chinese facilities consume an estimated 1,850 metric tons of selenium annually. Western industrial supply chains are doubly exposed to this bottleneck. High-strength steels and next-generation lithium-ion battery cathodes require high-purity manganese. Yet, Western manufacturers rely entirely on Chinese refining, while China controls the domestic allocation of the necessary selenium. Bypassing this bottleneck is technically and financially difficult. Alternative selenium-free refining processes exist but yield lower purity metal. They also require 20 to 30% higher capital expenditure, blocking rapid capacity substitution outside of China. The deployment of next-generation nuclear reactors faces a severe material bottleneck. High-temperature, gas-cooled, and molten salt reactors require high-purity isotropic graphite as a structural moderator. Global demand for this specialized material is projected to more than triple by 2030, reaching 39,500 metric tons. However, global purification capacity is expanding at only 3.4% annually. This divergence created a structural deficit starting in 2023. By 2030, the supply gap will reach 18,500 metric tons, threatening to delay reactor deployments by up to 48 months. Supply chain for nuclear-grade graphite is highly consolidated. 3 producers control over 77% of global purification capacity, with Japan's Toyo Tanso leading the market. Geographically, over 53% of global capacity is concentrated in Japan. This concentration exposes Western reactor developers to severe export control risks and supply chain shocks. The primary bottleneck is the extreme purification process required to reach an equivalent boron content of less than 1 part per million. This requires injecting corrosive halogen gases at temperatures exceeding 2,800 degrees Celsius. These specialized purification lines are currently operating at over 92% capacity. There is virtually no spare capacity to absorb the projected demand spike from commercial reactor rollouts. The graphite bottleneck is worsened by the harsh physics of neutron irradiation. Inside a reactor core, isotropic graphite undergoes severe dimensional changes over time. The material initially shrinks, reaching a minimum volume change of -2.1%. It then reverses, swelling rapidly to +7.5%, which causes internal microcracking and structural failure. Simultaneously, neutron bombardment degrades the graphite's thermal conductivity by over 60% within the first 5 displacements per atom. This rapid degradation limits the operational lifespan of core components. Consequently, these massive graphite blocks are not permanent assets. They must be completely replaced every 6 to 8 years, creating a continuous demand loop that competes directly with new reactor construction. Advanced semiconductor packaging is facing a severe material deficit. Epoxy molding compounds protect integrated circuits from physical and chemical degradation. However, the thermomechanical performance of these compounds is entirely dependent on high-purity phenolic curing agents. A structural supply deficit emerged in 2021. Global demand for high-purity cresol novolac resins reached 38.5 kilotons, exceeding the effective synthesis capacity of 36.0 kilotons. This imbalance has caused procurement lead times to quadruple. Average lead times escalated from 12 weeks in 2019 to 52 weeks by 2025. The underlying chemical synthesis capacity is highly inelastic. Building the required high-vacuum fractional distillation columns requires massive capital expenditure. Consequently, global capacity is growing at just over 2% annually, failing to match demand. The supply chain for these critical curing agents is highly consolidated. Japan holds a near monopoly, controlling 58% of global orthocresol isolation and 62% of advanced novolac resin synthesis. This concentration creates an acute single point of failure for advanced packaging. The United States represents a critical vulnerability, holding only a 4% share of global synthesis capacity. Domestic fabrication facilities remain entirely dependent on trans-Pacific chemical shipments. The barrier to entry for new producers is exceptionally high. Synthesis requires reducing ionic impurities like sodium and chloride to under 1.0 part per million. Exceeding this threshold causes galvanic corrosion of submicron copper interconnects, destroying the chip. This extreme purity requirement prevents rapid capacity substitution outside of established Japanese facilities. This chemical deficit is directly driven by the rapid scaling of high-performance computing and artificial intelligence hardware. Advanced packaging architectures, like three-dimensional stacked dies, require massive volumes of high-performance molding compounds. Resin consumption intensity for advanced packaging is projected to reach 415 grams per square meter of silicon by 2026. This represents a 97.6% increase from 2020 levels. The physical driver is the need to control thermal expansion. To prevent wafer warpage and microcracking during high-temperature reflow, the coefficient of thermal expansion must be reduced from 12.5 to 5.5 parts per million per degree Celsius. Achieving this low thermal expansion requires an ultra-high cross-linking density that only pure Cresol-Novolac resins can provide. Meanwhile, legacy packaging resin intensity remains flat, proving that the bottleneck is entirely concentrated at the leading edge of silicon integration. Advanced industrial water purification is facing a severe materials science crisis. Thin-film composite reverse osmosis membranes rely on per- and polyfluoroalkyl substances to achieve uniform, defect-free active layers. Proposed environmental bans on these persistent chemicals threaten to dismantle the supply of ultra-pure water required for semiconductor fabrication. Fluorine-free alternative membranes exhibit severe thermodynamic instability during manufacturing. After 5,000 hours of continuous testing, the salt rejection rate of these alternative membranes drops to 95.20%. This represents a 17-fold increase in solute passage compared to standard membranes. Simultaneously, the flux rate of fluorine-free membranes collapses by 45.2% due to rapid organic fouling. Standard membranes experience only a 5.3% decline over the same period. This degradation directly threatens the continuous operation of high-yield semiconductor fabrication facilities. To compensate for this performance deficit, a standard 100,000 cubic meter per day water plant must triple its downstream ion exchange resin volume. This modification dramatically increases capital expenditure and operational energy demands. Simple material substitution is currently chemically non-viable. The regulatory timeline is colliding directly with industrial reality. In 2024, over 56% of global membrane manufacturing capacity relies on per- and polyfluoroalkyl substances. This leaves 48,500,000 square meters of annual production exposed to impending bans. By the projected 2028 regulatory phase-in, compliant fluorine-free capacity will reach only 28 million square meters. This creates a structural supply deficit of over 42% relative to Western industrial demand. The transition cannot be accelerated by capital alone. Industrial qualification for semiconductor-grade ultrapure water membranes requires 36 to 60 months of continuous testing. Consequently, alternative membranes developed today cannot be deployed at scale before 2028. This temporal mismatch threatens to halt advanced logic fabrication across Europe and North America.